December 19th, 1944. Tachikawa airfield, west of Tokyo. Lieutenant Colonel Fumio Niimi stood before the wreckage of an American B-29 Superfortress that had crash-landed near the Japanese coastline 3 days earlier. The bomber, its fuselage crumpled but largely intact, sat on the frozen concrete like a metallic corpse awaiting dissection. What Niimi and his engineering team would discover inside this aircraft would fundamentally alter their understanding of the industrial chasm between Japan and America. The bomber represented more than military hardware. Hidden within its aluminum skin lay a technological sophistication that Japanese engineers had theorized about but never successfully implemented. Most jarring of all would be the pressurization system, a network of regulators, valves, and sealed compartments that allowed American crews to breathe normally at altitudes where Japanese pilots struggled for every breath through crude oxygen masks that froze at extreme altitude. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By late 1944, Japan's air defenses had encountered B-29 Superfortresses on dozens of raids. Japanese fighter pilots reported a disturbing pattern. The silver bombers cruised effortlessly at altitudes between 30,000 and 33,000 feet, heights where Japanese interceptors gasped for power. Pilots climbed desperately toward the American formations, their engines overheating, performance deteriorating, only to find themselves unable to sustain combat at those altitudes. The B-29 featured the first fully pressurized cabin system in a production bomber, with pressurized compartments that provided a comfortable environment for the crew at high altitude. 3 separate pressurized compartments meant that the crew of 11 could cruise at the plane's service ceiling of 31,800 feet without needing oxygen masks. Japanese aircraft had nothing comparable. The Koku Gijutsu Kenkyujo, Japan's Air Technical Research Institute based at Tachikawa, represented the pinnacle of Japanese aeronautical engineering. When word reached Tokyo that a relatively intact B-29 had been recovered, the institute immediately dispatched its most experienced engineers. Among them was Lieutenant Colonel Niimi, a specialist in high-altitude aircraft systems who had worked on Japan's experimental pressurization projects since 1941. Niimi had studied reports from fighter pilots who engaged B-29 formations. One account particularly troubled him, from Captain Teruhiko Kobayashi of the Imperial Army's 244th Sentai. Kobayashi's unit had intercepted B-29 seconds attacking the Musashino aircraft plant near Tokyo. His pilots climbed to 28,000 feet, engines screaming at maximum power. When they finally reached the bomber's altitude, Kobayashi reported that his own breathing came in ragged gasps despite his oxygen mask. His vision narrowed. His fingers, numb with cold despite electrically heated gloves, could barely manipulate the gun triggers. Meanwhile, through the B-29's clear nose sections, Kobayashi had glimpsed American crews moving about their stations, apparently comfortable, coordinating their defensive fire with methodical precision. Some appeared to be eating. One bombardier waved mockingly. The psychological impact was devastating. Japanese pilots were suffering while their enemies operated in shirt-sleeve comfort. The captured B-29 that awaited Niimi's team at Tachikawa had been designated B-2940BW, serial number 42-24621. It had been part of a formation attacking targets on Kyushu, when mechanical problems forced the crew to turn back. Damaged by flak and with 2 engines failing, the pilot attempted an emergency landing on what he thought was a relatively flat field. The landing gear collapsed on impact. The fuselage buckled. But unlike most B-29 seconds that crashed in Japan, this one did not burn. The crew survived and was taken prisoner. The aircraft, despite significant structural damage, remained remarkably intact. The B-29 featured the first ever fully pressurized nose and cockpit in a bomber, with an aft area for the crew also pressurized. Since the bomb bays were not pressurized, a pressurized tunnel was devised to connect the fore and aft crew areas. This was the system Niimi needed to examine. December 20th brought the first detailed inspection. Niimi's team numbered 12 engineers, each specializing in different aircraft systems. They began with external documentation, photographing every aspect of the wreckage before any components were disturbed. The B-29's sheer size impressed them immediately. The fuselage diameter exceeded anything in Japanese production. The wingspan stretched 141 feet. Fully loaded, intelligence suggested, these bombers weighed over 60 tons. But size alone did not explain the B-29's dominance. Niimi ordered his team to begin systematic disassembly, starting with the forward pressurized compartment. They needed to understand how Americans had solved problems that had defeated Japanese engineers for 3 years. The forward crew compartment extended from the nose to just aft of the wing's leading edge. When engineers carefully removed access panels, they discovered a revelation. The compartment was not merely sealed, it was engineered as a pressure vessel. The control system for the pressurization was designed by WWII Research Manufacturing Company. Every seam incorporated specialized gaskets. Doors featured elaborate locking mechanisms with rubber seals. The entire structure had been designed from the beginning to withstand significant pressure differential. Japanese engineers had attempted cabin pressurization in experimental aircraft. The Tachikawa SS-1, completed in 1943, had tested pressurization concepts. To speed up work, parts of the Lockheed Type LO were used, including wings, rear fuselage section and tail surfaces. The SS-1 was completed in May 1943, but the SS-1's pressurization system proved unreliable, maintaining pressure for only brief periods before seals failed or compressors overheated. The American system before Niimi operated on entirely different principles. A complex network of ducting drew compressed air from engine-driven superchargers, cooled it through heat exchangers, and distributed it throughout the pressurized compartments. Pressure regulators maintained cabin altitude at approximately 8,000 feet, even when the aircraft flew above 30,000 feet actual altitude. Outflow valves precisely controlled air exhaust to maintain constant pressure regardless of the bomber's altitude. Engineer Takeshi Yamamoto examined the pressure regulators with growing amazement. These were not crude mechanical devices, requiring constant adjustment. They were precision instruments, automatically maintaining pressure within narrow tolerances. The regulator mechanisms incorporated springs, diaphragms, and valves machined to tolerances measured in thousandths of an inch. Any fluctuation in cabin pressure triggered immediate compensating adjustments. More impressive was the system's redundancy. Multiple pressure sources ensured that failure of one engine's supercharger did not compromise cabin pressurization. Backup regulators provided safety if primary systems failed. Warning instruments alerted crews to pressure loss before it became dangerous. The entire system had been designed, assuming components would fail, engineering reliability through redundancy rather than hoping for perfection. Japanese aircraft design followed opposite principles. Systems were kept simple to facilitate field maintenance and reduce manufacturing complexity. Redundancy added weight and complexity that resource-constrained Japanese industry could not afford. If a system failed, skilled mechanics adapted and repaired it. The American approach assumed systems would fail and engineered solutions in advance. The pressurized tunnel connecting forward and aft crew compartments particularly fascinated Niimi. This tube, approximately 34 inches in diameter and 11 feet long, ran above the bomb bays. It allowed crew members to crawl between compartments while the aircraft operated at altitude. The tunnel's construction demonstrated manufacturing precision. Japanese factories could not match. Its cylindrical walls were formed from aluminum panels rolled to exact curvature. Longitudinal seams were welded, then ground smooth and inspected for pressure integrity. End flanges incorporated gasket grooves machined to specifications, ensuring airtight seals. Japanese attempts at similar structures had failed repeatedly. Forming cylindrical pressure vessels required specialized equipment and quality control beyond most. Japanese manufacturers' capabilities. Welds developed microscopic cracks under pressure cycling. gaskets compressed unevenly, allowing leaks. The Americans had solved these problems through superior manufacturing rather than superior design. On December 22nd, Niimi's team examined the environmental control systems. The B-29 did not simply pressurize the cabin, it controlled temperature and humidity. Heat exchangers cooled compressed air before distribution. Heating elements warmed specific crew stations. A ventilation system circulated air, preventing carbon dioxide buildup and maintaining crew alertness. At 30,000 feet, outside air temperature dropped to 40 degrees below zero or colder. Japanese pilots endured this cold despite electrically heated flight suits that often malfunctioned. Oxygen masks froze, fingers went numb, instruments became difficult to read. B-29 crews operated in comfortable 70-degree temperatures, their efficiency undiminished by environmental stress. The psychological dimension of this disparity troubled Niimi deeply. Japanese military doctrine emphasized spirit over materiel, dedication over comfort. Pilots were taught that superior morale compensated for inferior equipment. Yet here was evidence that Americans simply engineered away problems, rather than expecting crews to overcome them through determination. Which approach would prove superior in sustained warfare? Niimi documented another disturbing discovery. The B-29's pressurization system had been designed for ease of maintenance. Pressure regulators could be replaced in minutes using simple tools. Gasket kits standardized replacement seals. Ducting connections used quick disconnect fittings, rather than requiring careful fabrication. An adequately trained mechanic could maintain the system without specialized knowledge. Japanese experimental pressurization systems demanded skilled technicians who understood the principles involved and could adapt repairs to specific circumstances. Parts were often hand-fitted. Adjustments required experience and judgment. The American system eliminated the need for such expertise by building precision into the components themselves. By December 24th, Niimi's preliminary report to Imperial General Headquarters acknowledged painful realities. The B-29's pressurization system represented manufacturing capabilities Japan did not possess. Even if Japanese engineers obtained complete technical drawings, producing the components at scale would prove impossible given current industrial capacity. The materials alone presented insurmountable challenges. Alloys and other materials new to the Soviet Union had to be brought into production when they later attempted to copy the B-29. Japan faced identical problems. The aluminum alloys used in B-29 construction, the high-temperature gasket materials, the specialized lubricants for pressure regulators, all exceeded Japanese metallurgical capabilities. Developing equivalent materials would require years of research, while American bombers devastated Japanese cities with impunity. More fundamentally, the B-29 demonstrated systematic industrial organization that Japanese factories had not achieved. Every pressurization component was manufactured to specifications, ensuring interchangeability. A pressure regulator from one B-29 would install directly into any other B-29 without adjustment. Gaskets, valves, ducting sections, all were standardized and mass-produced. Japanese aircraft production relied heavily on skilled craftsmen who adapted components to specific airframes. No two Japanese aircraft were truly identical. Field maintenance required experienced technicians who could modify parts as needed. The American approach eliminated such variability through precision manufacturing, enabling rapid production by less skilled workers and simplified field maintenance. The examination continued into the new year. By January 1945, Niimi's team had compiled over 300 pages of technical documentation. They had photographed every pressurization component. They had measured tolerances, documented materials, sketched systems. They understood how the B-29's pressurization worked in exact technical detail. Yet this knowledge provided no solution. Understanding American engineering did not grant Japan the industrial capacity to replicate it. The gap was not merely technological, but organizational and infrastructural. American factories possessed precision equipment, quality control systems, trained workforces, and material abundance that Japanese industry could not match while simultaneously fighting a losing war. Niimi's report to his superiors contained a section that would later be classified and hidden from general knowledge. He wrote that Japan's attempts to develop high-altitude interceptors incorporating pressurization had been misguided. The Nakajima Ki-87 was developed in response to American B-29 Superfortress raids on the home islands, following up on earlier research into boosting a large radial engine with an exhaust-driven turbo supercharger, which had begun in 1942. The Ki-87 was a high-altitude, heavily armed fighter, powered by a single 2,400 horsepower turbo supercharged engine with an estimated 440 mile/hour top speed, but engine problems delayed production and only one prototype was produced. The problem was not Japanese engineering skill. The problem was that Japan lacked the industrial foundation to produce reliable pressurization systems, advanced superchargers, and precision components at the scale needed to make a difference. By the time Japanese industry developed these capabilities, the war would be over. Other Japanese fighters designed specifically to intercept B-29 seconds faced similar limitations. The Tachikawa Ki-94I seemed promising, with an estimated top speed of 450 miles/hour, and an order was placed for 18 service test aircraft, but the first flight was scheduled for August 18, 1945, 3 days after Japan surrendered. These aircraft remained paper dreams, while American bombers operated with impunity. Even Japan's most advanced operational fighter, the Nakajima Ki-84 Hayate, struggled against B-29 seconds despite impressive performance. The Ki-84's operational ceiling enabled it to intercept high-flying B-29 Superfortress bombers, though it lacked sufficient high-altitude performance. The Hayate could reach 35,000 feet in theory. In practice, degraded fuel quality, maintenance problems, and poor pilot training meant few Ki-84 seconds achieved design performance. More fundamentally, even successful interceptions rarely brought down B-29 seconds. The bomber's rugged construction absorbed punishment that would shred Japanese aircraft. 2 crew areas, fore and aft, were pressurized and connected by a long tube over the bomb bays, allowing crew members to crawl between them. The tail gunner had a separate pressurized area that could only be entered or left at altitudes that did not require pressurization. This compartmentalization meant battle damage to one section did not necessarily compromise the entire crew's survival. Japanese pilots reported firing entire ammunition loads into B-29 seconds, scoring multiple hits, only to watch the bombers continue toward their targets. Damaged B-29 seconds with engines shut down, trailing smoke, still made it back to their bases in the Marianas. The psychological impact on Japanese pilots was crushing. They were sacrificing their lives in desperate ramming attacks, while American bombers absorbed damage and returned to fight again. The implications of the B-29's pressurization system extended far beyond the immediate challenge of intercepting high-altitude bombers. In February 1945, Niimi was ordered to brief senior officers at Imperial General Headquarters on his findings. The meeting took place in an underground bunker, protected from the increasingly frequent B-29 raids that now struck Tokyo almost nightly. Niimi's presentation lasted 2 hours. He explained the pressurization system's components, its redundancies, its manufacturing requirements. He showed photographs of pressure regulators, cross-sections of sealed compartments, diagrams of air distribution networks. The officers listened in silence. When Niimi finished, Major General Aresue Seizo, Chief of Intelligence, asked a single question. "Can we build this?" Niimi's answer was careful, but devastating. Japan could theoretically design similar systems. Japanese engineers understood the principles involved, but actually manufacturing pressurization systems at the scale needed to make a strategic difference would require industrial capabilities Japan no longer possessed. The bombing campaign had destroyed critical factories, Skilled workers had been killed or dispersed. Material shortages worsened daily. Even if Japan somehow obtained unlimited resources, developing production capacity would take years. The general nodded slowly. He had received similar reports about other captured American equipment. The pattern was consistent. American military technology succeeded not through revolutionary design, but through superior manufacturing. The United States had engineered an industrial system capable of producing complex equipment in quantities that overwhelmed opponents, regardless of tactical skill or strategic brilliance. By March 1945, Japan's situation had become desperate. On the night of March 9th to 10th, 334 B-29 seconds attacked Tokyo with incendiary bombs from low altitude. The raid killed approximately 100,000 people and destroyed 16 square miles of the city. Niimi's laboratory at Tachikawa, along with the captured B-29 he had examined, was damaged in subsequent raids. Much of his documentation survived, but the physical aircraft was largely destroyed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The examination of the captured B-29 had revealed truths that Japanese military leadership struggled to accept. American superiority derived not from individual brilliance but from systematic organization. The B-29's pressurization system exemplified this principle. The crew would enjoy, for the first time in a bomber, full pressurization comfort. This first-ever cabin pressure system for an Allied production bomber was developed for the B-29 by WWII Research. WWII Research Manufacturing Company had specialized in developing aviation systems since the late 1930s. In 1939, Cliff Garrett established a small research laboratory to conduct air research on the development of pressurized flight for passenger aircraft. By the time B-29 production began, Garrett possessed years of experience in pressurization technology, supported by extensive testing and iterative development. Japan had no equivalent organization. Japanese aircraft companies designed complete aircraft but rarely specialized in individual systems to the degree American companies did. Subcontractors existed, but quality control and standardization remained inconsistent. The systematic development of specialized technologies, refined through multiple iterations and supported by extensive testing, was not how Japanese industry operated. The examination of the B-29's pressurization system also revealed American assumptions about warfare that differed fundamentally from Japanese thinking. The American system assumed long missions requiring crew comfort to maintain effectiveness. It assumed aircraft would operate repeatedly rather than being expended. It assumed maintenance would be performed by adequately trained but not necessarily expert mechanics using standardized replacement parts. Japanese doctrine emphasized different priorities. Aircraft were kept simple to facilitate rapid production and field maintenance by skilled craftsmen. Long-range missions were rare. Most combat occurred relatively close to Japanese-held territory. Crew comfort was considered secondary to combat effectiveness. If pilots could endure harsh conditions through superior spirit, why waste resources on environmental control systems? By mid-1945, these philosophical differences had produced measurable outcomes. American B-29 crews flew multiple missions, their effectiveness sustained by comfortable working conditions. Japanese pilots flew until killed, their declining performance accelerated by environmental stress and inadequate rest. American bombers returned to base for systematic maintenance. Japanese fighters were patched together by mechanics improvising with whatever materials remained available. The Soviet Union would later face identical challenges when attempting to replicate the B-29. On November 11, 1944, the General H.H. Arnold Special was damaged during a raid and forced to divert to Vladivostok in the Soviet Union, where the crew was interned. On November 21, 1944, Ding Hao was also forced to divert to Vladivostok. Stalin ordered Tupolev to duplicate the Superfortress as quickly as possible. The reverse engineering effort involved 900 factories and research institutes, which finished the design work during the first year, and 105,000 drawings were made. Soviet engineers examining the interned B-29 seconds encountered the same revelations that had troubled Niemi. The pressurization system's complexity and manufacturing precision exceeded Soviet capabilities. In many ways, the biggest challenge of the B-29 process was in its electronic systems, particularly the central fire control system that used General Electric analog computers to aim and fire weapons remotely. The CFCS was vital because the B-29 was pressurized and large apertures for the guns were out of the question. The Soviets had resources Japan lacked. Stalin's orders were promulgated, tasking the Tupolev Design Bureau to copy the B-29 and put it into production. An extremely detailed instruction placed the weight of responsibility on Tupolev's shoulders, but also placed the whole of Russian government and industry behind him. Even with total state support and 2 years of intensive effort, Soviet engineers struggled to replicate American manufacturing precision. The Soviet Union used the metric system and so sheet aluminium in thicknesses matching the B-29's U.S. customary measurements was unavailable. The corresponding metric gauge metal was of different thicknesses. Alloys and other materials new to the Soviet Union had to be brought into production. Extensive re-engineering had to take place to compensate for the differences. Japan faced all these challenges without the Soviet Union's advantages. Japanese industry was being systematically destroyed by the very aircraft they were attempting to understand. The circular logic was inescapable. To defend against B-29 seconds, Japan needed high-altitude interceptors with pressurization and advanced systems. To build such aircraft required industrial capabilities being destroyed by B-29 raids. The bombing campaign's success derived partly from the fact that American bombers operated beyond effective Japanese countermeasures, which could not be developed because the bombing prevented the industrial development necessary to create them. Niemi documented another aspect of the B-29's pressurization that revealed American engineering philosophy. The system had been designed for maintainability in forward operating bases with limited facilities. Each B-29 had to be modified in order to become combat ready. Every electrical connection, a total of 586,000 per aircraft, had to be disassembled and resoldered, as faulty connectors had been installed initially. The engines themselves had to be pulled out of the aircraft and either replaced or modified. Despite initial production problems, the B-29's design allowed systematic correction. Standardized components meant replacements could be manufactured and distributed efficiently. Maintenance procedures could be documented and taught. Problems could be identified and solved across the entire fleet. The aircraft improved in service because American industrial organization supported continuous refinement. Japanese aircraft rarely improved after entering production. Once manufacturing began, changes were difficult to implement. Parts standardization remained limited, so modifications often required individual fitting. Knowledge remained with specific mechanics rather than being systematically documented and distributed. Aircraft performance frequently declined in service as maintenance standards deteriorated under wartime pressure. By April 1945, American bombers had shifted tactics. Rather than high-altitude precision bombing, B-29 seconds now attacked at night from medium altitudes with incendiary weapons. On April 1st, a night precision bombing raid was flown against the Nakajima engine factory in Tokyo by 121 B-29 seconds, and 3 similar attacks were conducted against engine factories in Shizuoka, Koizumi and Tachikawa on the night of April 3rd. The Tachikawa raid destroyed much of the research facility where Niemi had examined the captured B-29. Ironically, the shift to low-altitude bombing meant the B-29's high-altitude pressurization capability was less critical for many missions. But the system's existence had forced Japan to develop high-altitude defenses that never became effective. Resources were diverted to interceptors optimized for extreme altitude when American bombers increasingly struck from medium altitude where Japanese fighters performed better. The pressurization system's mere existence had shaped Japanese defensive strategy, even when not tactically employed. The examination of the captured B-29 had also revealed connections between different American technologies. The pressurization system worked in conjunction with the remote-controlled gun turrets. The B-29 featured a General Electric Company Model 2, CFR-55B1 centralized fire control system, which transformed bomber defensive gunnery from a loose collection of independent guns into an integrated gunnery system. Because the crew compartments were pressurized, gunners could not occupy traditional exposed positions. Remote turrets were necessary, which required computerized fire control, which required reliable electrical systems, which required quality manufacturing. Each advanced feature depended on others. Japanese engineers attempting to copy individual systems discovered they could not be separated. Pressurization required remote turrets. Remote turrets required computers. Computers required reliable electrical components. Reliable components required precision manufacturing. Precision manufacturing required specialized equipment, trained workers, and quality control systems. The entire structure was interdependent. This interdependence explained why Japan could not simply copy specific American innovations. Japanese industry would need transformation at every level simultaneously. Aircraft designers needed different training. Manufacturing facilities required new equipment. Supply chains needed reorganization. Quality control demanded systematic implementation. Workers needed retraining. Even procurement and maintenance doctrines required revision. The scope of necessary changes exceeded what could be accomplished during wartime. Lieutenant Fumio Niimi survived the war. In 1946, American occupation forces interviewed him extensively about his examination of the captured B-29. The United States Strategic Bombing Survey conducted comprehensive examinations of Japanese war production. Teams of American engineers toured Japanese aircraft factories, documenting production methods and assessing industrial capabilities. Niimi's documentation proved valuable in understanding why Japanese air defenses had failed. The interviews revealed that Japanese engineers had understood intellectually what was required to match American capabilities. They were not ignorant or incompetent, but understanding and implementation were separated by an industrial chasm too wide to cross during wartime. Niimi told American interrogators that examining the B-29's pressurization system had been professionally devastating. It demonstrated that Japanese industry was not merely behind American industry in degree, but in kind. The gap was not years, but generations. The first batch of 2-4 rolled off the assembly line on schedule in 1947. It flew for the first time on May 19, 1947. The Soviet Union, with vastly greater resources than Japan and freedom from aerial attack, required 2 years to reverse engineer the B-29, even with multiple intact examples available for study. Japan, while being bombed constantly, with limited resources and inferior industrial base, had no realistic prospect of developing comparable capabilities. The pressurization system represented a specific technological challenge, but Niimi's examination revealed broader truths. American military success derived from industrial organization that turned adequate designs into overwhelming material superiority through quantity and reliability. Japanese military success required tactical brilliance and individual excellence to compensate for material inferiority. When American industry reached full production capacity, tactical skill became insufficient. The mathematics were brutal. By summer 1945, American factories were producing B-29 seconds, at rates approaching 16 aircraft daily from multiple production facilities. Boeing's plant in Seattle produced 6,981 B-17 seconds by the time production ended in April 1945. Douglas Aircraft in Long Beach produced 3,000 B-17 seconds between July 1942 and July 1945. Lockheed Vega in Burbank built 2,750 B-17 seconds between August 1942 and August 1945. The B-29 production, while smaller in total numbers, represented even greater industrial achievement given the aircraft's complexity. Each B-29 contained approximately 500 tons of raw materials transformed through hundreds of thousands of man-hours into a functioning weapons system. The pressurization system alone required components from dozens of specialized suppliers, each manufacturing to tolerances, ensuring interchangeability. The supply chain's complexity exceeded anything Japanese industry had organized. Japanese aircraft production peaked at approximately 2,800 aircraft monthly in mid-1944, then declined steadily as bombing destroyed factories and disrupted supply chains. By early 1945, monthly output had fallen from over 2,500 airframes in May 1944 to barely 1,500. Even at peak production, quality was declining. Engines failed prematurely. Airframes showed construction defects. Materials were substituted with inferior alternatives as shortages worsened. American production increased throughout 1945. Aircraft became more reliable as manufacturing problems were identified and corrected. Supply chains functioned efficiently despite global distribution. Maintenance improved as crews gained experience. The industrial system was self-reinforcing. Success enabled expansion, which generated more success. The examination of the B-29's pressurization system had taught Niimi that modern industrial warfare was won not by superior courage or tactical skill, but by superior organization. The American military had recognized this before the war began. In 1940, Boeing submitted an advanced design for a four-engine bomber with a pressurized fuselage, which the Air Corps chose for production as the B-29. The B-29 program would become the most expensive of the war, outpacing the development of the atomic bomb by more than $1 billion. American planners had invested $3 billion developing the B-29, more than the Manhattan Project's cost. This investment reflected confidence that industrial capacity would prove decisive. Japanese planners had no equivalent resources to invest, even if they had recognized the strategic importance of such programs. The war was lost industrially before tactical operations began. By August 1945, when atomic bombs delivered by B-29 seconds ended the war, Japanese engineers had examined multiple examples of American equipment and reached consistent conclusions. American military technology succeeded through systematic application of adequate engineering rather than brilliant innovation. Quality was built into manufacturing processes rather than depending on skilled craftsmen. Redundancy and standardization ensured reliability. Maintenance was simplified through interchangeable components. The entire approach assumed industrial abundance rather than resource scarcity. These lessons would shape Japan's post-war reconstruction. Engineers who had examined American aviation technology influenced post-war Japanese industrial development. Emphasis on precision manufacturing, quality control, and systematic engineering that characterized American turbo-supercharger production became hallmarks of Japan's post-war economic miracle. Former aviation engineers moved into civilian industries, applying hard-won understanding of advanced manufacturing techniques to automobiles, electronics, and other products. The captured B-29 that Niimi examined was largely destroyed in bombing raids before war's end. But the lessons it taught survived. Japanese engineers learned that matching American industrial capability required not just copying American products but transforming Japanese industrial organization. This transformation took 2 decades. By the 1960s, Japanese factories were producing automobiles and electronics, using precision manufacturing methods comparable to American standards. By the 1970s, Japanese manufacturers had refined these methods, developing production systems that improved on American mass production techniques. The pressurization system Niimi had studied so carefully in December 1944 became a symbol of the industrial transformation Japan required. It represented systematic engineering, precision manufacturing, and organizational discipline. These became foundations of post-war Japanese industrial success. The engineers who had examined captured American equipment understood that defeat was inevitable given industrial disparities. More importantly, they understood why, and in understanding created foundations for ensuring that industrial inadequacy would never again limit Japan's capabilities. Today, only two B-29 seconds remain airworthy, preserved and maintained by dedicated organizations. When these bombers fly at air shows, their Wright R-3350 engines producing that distinctive deep-throated roar, few spectators realize that hidden within engine nacelles are turbo superchargers, survivors of technology that helped end history's most destructive war. Even fewer realize that the pressurization systems these aircraft carried represented industrial capabilities that determined the war's outcome as decisively as any battle. The story of Japanese engineers examining captured B-29 pressurization systems ultimately demonstrates how industrial organization determined modern warfare's results. The precision manufacturing that produced reliable pressure regulators, the systematic testing that validated component performance, the quality control that ensured interchangeability, the supply systems that distributed replacements efficiently, these were the true weapons of strategic bombing. The pressurization system's technological superiority did not make American victory certain from the war's beginning, but once American industry reached full production, once B-29 seconds filled the skies over Japan operating at altitudes Japanese defenders could not effectively reach, defeat became inevitable. Lieutenant Colonel Fumio Niimi wrote in his final report to Imperial General Headquarters that examining the B-29 had taught him the most important military lesson. In modern industrial warfare, victory belongs not to those with the bravest soldiers or the most brilliant generals, but to those with the most effective industrial systems. Spirit and skill matter, but when opponents possess material advantages measured in orders of magnitude, courage becomes insufficient. The B-29's pressurization system, allowing crews to breathe comfortably at 30,000 feet, while Japanese pilots struggled with freezing oxygen masks far below, exemplified this reality with brutal clarity. When B-29 seconds cruised at extreme altitude over Japan, their pressurized compartments maintaining shirt-sleeve comfort while Japanese interceptors gasped for air below, they carried more than bombs. They carried proof that systematic industrial organization had become the decisive factor in modern warfare, and that American industrial might had reached levels no enemy could match. Japan never expected that the ability to breathe normally at high altitude would prove so strategically decisive. Once the silver bombers filled the skies beyond defensive reach, sustained by industrial systems that kept them flying mission after mission, there was nothing Japan could do to stop the inevitable conclusion. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.